Hello friends, let us start our journey into computational chemistry with Sulabh Shikshan. So before we start, I would like to brush up a few of the basic things from the sciences. Let us look into the universe around us, and in turn our life is nothing but an expression of space, matter and energy. Yes, space forms the most voluminous part of the universe around us. Space is the biggest contributor. Do you imagine hydrogen atom in front of you? It is just a single proton at the center and an electron revolving around this proton. And if you try to calculate the space present in this single atom of hydrogen, you will be baffled to see this figure. It's almost about 99.12 times 96% empty space. So much of a huge space. So most of the mass of hydrogen atom is situated at its center in the form of a proton, while the electron revolves at a very large separation as compared to the radius of the proton, and the radius of the electron is also very tiny, almost about 10 raised to minus 18 the order. It has not exactly been calculated so far what is the radius of an electron, but we definitely know the radius of a proton. And based on these, when we perform these calculations, we find out that this whooping figure, that 99.12 times 96% of the hydrogen atom is nothing but just empty space. And that is how we have to look into the matter. So be it a stone, be it a piece of metal, be it water, be it air, whatever it is maximally space, and then some part of it is matter. And associated with this space and matter is energy. Especially energy is associated with matter. Energy can be converted into matter, matter can be converted into energy through the famous Einstein's equation. That is what we know. So in a nutshell, what we have to keep in your mind is that the universe is an expression of space, matter and energy. And in turn, human life or any kind of life on this earth is also an expression of space, matter and energy. And as a chemist, we are much more interested into an interplay of this matter and energy. Rather than interplay of matter and energy, the relationships between matter and energy. We are more interested into matter. Let us move forward. What exactly is chemistry? Chemistry is nothing but the study of molecules, how these molecules are constructed, how these molecules are transformed from one form to the other form, or what are the properties of these molecules which may benefit us, or what are those properties which may prove to be harmful to us. So both way we are interested, either harmful properties or beneficial properties. So basically chemistry is nothing but the study of molecules with respect to construction, transformation and properties. And molecules make up the matter. That is why the significance of the first slide, where it says that as a chemist we are interested into matter, and matter is composed of molecules, ions and atoms. So let us move towards the next part. What exactly these molecules are? Molecules are collections of atoms, and atoms in turn are collections of positive particles and negative particles. I think there is no need for me to explain what these positive particles and negative particles are, because you know positive particles are protons, whereas negative particles are electrons. There are many subnucleonic particles or subparticles which make up these particles as well, but as a chemist we will confine our discussion to these positive particles and negative particles, that is protons and electrons only. Now how do molecules differ from each other? Because if the molecules do not differ from each other, you cannot say that this molecule is this one, this molecule is this one. So either in a strong sense of space and dimension on chemistry, we will just say that molecules differ because either different nuclei have the same positions in space, or the other way molecules can differ is that the same nuclei take different positions in space. So both way molecules can differ from each other. So you can distinguish one molecule from one other molecule. So some for example, water. If you say that okay, this hydrogen is situated at this place, oxygen is situated at this place, and another hydrogen is situated at this place, and you may say H2S. Oh, there is sulfur instead of oxygen, and then there are hydrogens at different spaces. So that is how either there can be changes in the nuclei I mean to say nuclei may be replaced with some other nuclei, or there can be changes in the positions of these nuclei in the space around us. So that is how molecules differ from each other. So let us move towards the next part, that is what exactly is theoretical chemistry. So theoretical chemistry tries to put forth theories and explanations for chemical observations and also guides the future experiments. The whole aim of this theoretical chemistry is to predict by using physical laws the structure, dynamics, bonding, reactivity, chemical properties, and spectroscopic response of molecular systems. And when you implement the methods which have been developed by theoretical chemistry in actual practice using digital computers, you call that field to be computational chemistry. So theoretical chemistry and computational chemistry, these are a little bit different from each other, but there may be some overlapping areas wherein a computational chemist may be little more interested in theoretical chemistry as well to develop new methods, or sometimes a theoretical chemist may be little more interested into actual computational chemistry for implementing the methods he has theorized. So ultimate aim of both of these is that given a set of nuclei and electrons, you should be able to tell the stability of your molecular system or say the chemical system. You should be able to predict their properties. You should be able to predict or say you should be able to go for structure activity relationships if you are given a set of nuclei and electrons. If you know the positions of these nuclei, if you know the kinds of these nuclei, and then you should be able to find out what might be the interactions developing at different molecules, or say what might be the energies associated with these chemical systems, or sometimes you might also be interested into the rates at which these reactions take place, or you might also be interested into the relative stability of these compounds. Now, what exact properties we are aiming at when we say that if you know the wave function or if you know the wave function of a molecular system, you may have the access to all the properties. So these properties include dipole moments, orbital energies, or say such as highest occupied molecular orbital, lowest unoccupied molecular orbital, or you may even get access to molecular electronic potential around that molecule. And as an important part, say properties. You may also calculate spectra of these molecules like say infrared spectra, UV visible, NMR, EPR, NMR, whatever it is. And you may also judge the relative reaction paths, rates and barrier heights which are of importance in chemical dynamics or chemical reaction dynamics or whatever, what course the reaction takes place. So in the next video, we will look into more details of this computational chemistry. Stay tuned.